By the end of today, you're going to have to answer a question that many people are currently avoiding, which is if a machine talks to you and reasons like you and can actually fool you in a conversation, do you still get to say that that machine does not have a mind? So that's one of the things we're going to tackle today. And we are going to continue this in service of our understanding of the human mind. But before we dive into the topics of the day, just a real quick note about the content of the lectures. So at this point, oftentimes in the course, some students start to wonder, why did I buy a textbook for this course? Because so far, very little from the textbook has been covered in the course. And the reason for that is because when I structure my courses, I basically have three types of lectures. So some of the lectures are going to be like the ones that we're doing today, the class meetings that we're having, where it's beyond the scope of what is covered in the book. It's things that I think are important, things that you will need to know, things that maybe the textbook just hasn't been able to catch up with, or just decided that's not the focus of what the textbook is going to be. So those are going to be some of the lectures where we go beyond what's in the textbook. Other times, however, we are going to cover very foundational topics in cognitive psychology. So, for example, we have a meeting coming up on attention, and that is going to go over a lot of what you are going to read in the textbook because it is so important. So, I do want you to see it in a variety of different ways. So, some of it will be things that you'll recognize that you read. Other versions will also have applications of these topics to the real world. So, how do you take things that we learn in attention and apply them to navigating the real world? How do you take things that we learn about decision making and apply them to, interacting with other individuals? So there's a variety of different types of meetings that we're going to have in class. So just so that you know, the textbook is important. We are going to get to some topics straight out of the textbook, but I kind of find that laying this foundation right now gives you a really good place to start with and allows you to avoid kind of going off course because you know at the foundation what we're looking at. We're looking at the human mind, and we have a definite approach to use that everything else slots into. So the attention work that we take a look at is all the information processing approach. The perception work is all information processing. The decision making is all information processing. So if we can lay that foundation right off the bat, it's going to anchor you for the rest of the semester. So before we get to any of wrapping up our look at representation, I did want to bring up one example. I mentioned this last time, and it was from a discussion that we had where we were talking about cognition. We were talking about whether artificial intelligence would ever be able to replicate human intelligence. And one of the points that was made was that humans have emotions, and emotions are part of cognition. And sometimes you have negative emotions, and that affects how you think and how you process information. And sometimes you have really positive emotions, and your processing of information will literally change. And then sometimes those positive emotions are a little too positive and they get a little scary. But I mentioned the impact that emotions can have on your reasoning. And I mentioned the author and former FBI hostage negotiator, Chris Voss. This is going to be an excerpt from his book on negotiating called Never Split the Difference. If you are ever looking for a really accessible book about how to very effectively interact with other human beings, I highly recommend this book. And we're going to just hear an excerpt from this about a time when Chris Voss went to a Harvard Business School class, and the excerpt is called "The Stupidest Person in the Room." And I would argue that it's not that he was the stupidest person in the room, but he was the least rational person in the room. And as we're going to see, that actually made him the most effective person in the room. So without any further ado,
the smartest dumb guy in the room. To answer my questions, a year later, in 2006, I talked my way into Harvard Law School's winter negotiation course. The best and brightest compete to get into this class, and it was filled with brilliant Harvard students getting law and business degrees, and hotshot students from other top Boston universities, like the Massachusetts Institute of Technology and Tufts. The Olympic trials for negotiating. And I was the only outsider. The first day of the course, all 144 of us piled into a lecture hall for an introduction, and then we split into 4 groups, each led by a negotiation instructor. After we'd had a chat with our instructor, mine was named Sheila Heen, and she's a good buddy to this day, we were partnered off in pairs and sent into mock negotiations. Simple. One of us was selling a product, the other was the buyer, and each had clear limits on the price they could take. My counterpart was a languid redhead named Andy, a pseudonym, one of those guys who wear their intellectual superiority like they wear their khakis, with relaxed confidence. He and I went into an empty classroom overlooking one of those English-style squares on Harvard's campus, and we each used the tools we had. Andy would throw out an offer and give a rationally airtight explanation for why it was a good one, an inescapable logic trap, and I'd answer with some variation of, "How am I supposed to do that?" We did this a bunch of times until we got to a final figure. When we left, I was happy. I thought I'd done pretty well for a dumb guy. After we all regrouped in the classroom, Sheila went around the students and asked what price each group had agreed on, and then wrote the result on the board. Finally, it was my turn. "Chris, how did you do with Andy?" she asked. "How much did you get?" I'll never forget Sheila's expression when I told her what Andy had agreed to pay. Her whole face first went red, as if she couldn't breathe, and then out popped a little strangled gasp like a baby bird's hungry cry. Finally, she started to laugh. Andy squirmed. "You got literally every dime he had," she said, "and in his brief he was supposed to hold a quarter of it back in reserve for future work." Andy sank deep in his chair.
All right, so this is an example of how emotions are heavily involved in your cognition. So Andy came there with very rational explanations, and if you've ever taken courses in negotiation, you'll know things about the minimum acceptable offers, and you'll know things about like the range that you have to offer. And you start off high, but then you go a little bit lower, but then you want concessions, and all the sort of rational things that you're supposed to do that will oftentimes work when you're in with another person who's rational. However, Chris Voss outperformed everybody by simply asking every single time the offer was made, how am I supposed to do that? How am I supposed to agree to that? Basically triggering emotions that let you feel that this was unfair, my offer to this person was unfair. And then his question of asking, how am I supposed to do that, made you solve his problem. Rather than him throwing out a number, you would be the next person to throw out a number. So all of that kind of emotional processing that goes on in the real world was what made Chris Voss such a master FBI negotiator, and basically was the reason why the FBI used to use rational business tactics when it was negotiating with, for example, hostage takers, and now they've switched over to more emotional tactics when negotiating with them, and their success rates have increased. All right, so that was just a little brief aside. Again, never split the difference. Highly, highly recommend it. But now we're going to move on again to our understanding or our exploration of the human mind. So once again, just to remind you, we are going to see time and time again that your human mind is not the brain. Knowledge of the brain can inform our knowledge of the human mind, as we're going to see, but importantly, it is not equal to the brain. And that means that there can be a variety of different things that make up our mind that go beyond our skull, go beyond where our brain resides. And that's what we're trying to explain. So if your mind is not your brain, then that also opens up the possibility that there might be other minds that are actually not brains. Specifically, there might be artificial minds, artificial intelligence, and this might be an alternative intelligence that is capable of actual thought, actual reasoning, actual cognition. So that's what we're going to tackle today. And we're going to start off with representation and do a quick recap on our basic approach, the information processing system approach. We're going to recap Marr's tri-level hypothesis, talk about what is representation, and then we're going to go to the Pandemonium model. And we're going to finish up our look at the Pandemonium model by taking a look at how it deals with another font, and then taking a look at some of the questions that are suggested when you have a model that is very useful. It oftentimes gives you insights that you would not normally have thought of. Then we're going to switch to artificial or alternative intelligence. First off, we're going to talk about why is this important to cognitive psychology. So why are we introducing it so early in a course on cognitive psychology? We'll introduce the physical symbol system hypothesis. And then we're going to take a look at some of the work done by Alan Turing, specifically his proof of what a Turing machine can do, and we'll talk about what that is. And then finally, we'll end with a very famous test of whether something has a mind, which is the Turing test. So just a quick recap of what we went over in our last meeting. So the information processing approach views your mind as an information processing system. So it takes in inputs from the outside world and combines those inputs in different ways. So it represents these inputs and then works on those representations to make a final decision or a final cognition in terms of what you should do. And if we want to understand an information processing system like the mind, David Marr suggested that we need to understand it at 3 levels. So once we have a computational, representational, implementational level explanation of the mind, cognitive psychology will be done. We'll be finished and we'll have to find something else to do. That's not going to happen for a while because the computational level, not even that is finished. So that is the problem that is faced. That is what can humans do, or as we're going to see for AI, what can AI do? What can your mind basically do? Representational level, what are the strategies that might be used? And these have to be in computational terms. That means these have to be in, here's the information that comes in, here's how the information is manipulated, here's the information that goes out. And then finally, for a complete understanding, you do need the implementation level, which is how is this actually done in a real physical entity? How is this made in the real world out of real stuff? So representations, these are the hypothetical internal cognitive symbols that your mind uses to represent external reality. And one of the big challenges of cognitive psychology is that there are a variety of different representations, a variety of different cognitive symbols that are possible to represent any external reality. So we as cognitive psychologists, one of our basic challenges is to figure out what representations is our mind using. So different ways of representing the concept of two, different ways of representing the spatial layout of the United States. And if you have an external reality, you can have internal symbols that are imagery symbols, meaning that the symbols map onto the physical characteristics of the actual external reality. Or you can have propositional symbols, propositional representations, where it's a language kind of statement form of representation representing the same external reality. And we'll talk about that when we get to chapter 10. So in our look at the representational level, we took a look at how humans might recognize letters. This is something that we know that we can do. And we saw the template model, which basically says that that external reality is represented in an image processor, and then that image is searched for among a template. And if that image fits into a template, much like a jigsaw puzzle piece fits into its location, then the decision is made that we recognize that letter, and in this case, that letter would be R. The other model that we proposed, the other representational strategy, was the Pandemonium model by Selfridge, and that one had an image daemon that sent the representation of the external R to a TV screen in a room full of feature demons. 3 of them are really angry, so they have turned invisible. But the feature demons that turn invisible, they get angry and turn invisible because they see the symbol on their belly on that screen, and they call to complain to the cognitive demons. And then, depending upon how many complaints are made to each of these cognitive demons, that decision demon can decide, oh, the one with the most complaints is the R cognitive demon. We must be looking at an R. So that's where we left off last time. And what we're going to do this time is we're going to continue our look at this really simple, trivial behavior that we can do, recognize the letter R. And we're going to throw another challenge to these models. And we're going to ask about different fonts. What about different fonts? So again, we're going to start off at the computational level, just to make sure that our human minds can actually recognize different fonts. So much like last time, we'll just do an in-class speed demo for this. So when you see a letter that you recognize, just call it out. Okay, so we have now completed that part of the computational level. We know that we can recognize in that font R, F, Z, and P. Next, we go to the representational level, and we think about the strategy that may be used in computational terms. So, spoiler alert, this is where the template model really ran into difficulties when it was first proposed. Because in this case, according to the way that the template model works, and remember, this was based on, if you recall, one of the analogies that we use to understand the human mind is the mind as a computer. In order to understand letter recognition, they use the analogy of recognition as fitting into a template. So literally like a very mechanistic, you have this metal template that you're trying to fit these raised letters into, and that's how you recognize letters. So that's very important because what that means is that when you have this new font, this R, it gets sent to the image processor, and then the image processor is compared to that template. So we start up there at the top of the template, and we go all the way through, and we're looking for that match, we're looking for that match. We get to that point where we would have normally stopped. Last time, that's where we would have stopped. But that font does not fit into that template. So there's no match. So we keep going. We get to the end of the template. We haven't matched anything. And the decision is we don't know what we're looking at. We don't recognize it as a letter. Now, importantly, this template model has just failed to explain the computational level. We know we can recognize that letter R. The template model says that we can't recognize that letter R. That means that as it stands, this template model is not correct. It's not the strategy that we use. Now, does anybody have any idea how we could make this template model able to recognize this R? Mm-hmm. Multiple templates. So that was exactly the strategy that people used. And can anybody, does that kind of, it didn't sit well with theorists. Can anybody guess what was the major critique of multiple templates? Mm-hmm. Too much processing power, yes. It would take too long to go through each letter. So we wouldn't have the speed that we actually have. So recognizing that R did not take us very long whatsoever. And then anybody else think of criticism? So that is one, just the processing power that we have just doesn't match. Yep.
Maybe the different templates, making sure whichever ones would match, would be the different templates that they would use to recognize that specific R in a specific font.
Mm-hmm.
You know, like having the same letters that like are in the shape of the R. Maybe they would try to use the template that would have that type of.
Yeah. So you would need a new template for this font, right? You would need a complete new template for this font. Well, how many templates would we need in our modern society? We would literally need like hundreds of templates. Mm-hmm. Yeah, so handwriting would be illegible to us, not just the same person's handwriting over and over, but like just different people's handwriting. So you would need a template for every single font. You would need a template for every single person's handwriting that you ever could recognize. And then also, one of the last criticisms was if I showed you a new font, you don't need time to learn it. You don't look at it and say, okay, well, give me about half an hour, come back, and I will have learned what these letters are. No, you just take a look at it and you say, oh, that's an interesting way to do an R. That's an interesting way to do an F. So it's immediate. So this idea that we have multiple templates, we check through all of them, the processing power would just be through the roof. We need to develop new ones every single time we have a new template. All of those just kept piling on and on and on. And people said, you know what, template model is just not feasible. It's not, it can't be the representation that we're using. On the other hand, you go to the Pandemonium model with the demons, and in this case, remember that the feature demons, they get angry when they see something that looks like what's on their belly. So when that new font R is projected onto that image demon, and that gets sent up to the TV in the feature demon room, that first demon there with the vertical line still sees a vertical line in that R. It's not a clean vertical line, but his vertical line is still in that R. So he would still get angry. He would still go invisible. He would still call his cognitive demons that he's connected to. And then the next feature demon sees that curve in that R, even though it's a different font. So he disappears because he gets so angry, but not before calling his cognitive demons. That third feature demon doesn't see its particular feature in that TV screen. That fourth feature demon does, gets real angry, turns invisible, calls its cognitive demons, and then once again, the cognitive demons discuss amongst themselves, and cognitive demon R says, wow, I got three people, three feature demons complaining to me. Cognitive demon P says, I only got two people complaining to me. Cognitive demon F says, I only got the one person complaining. Cognitive demon Z doesn't even think anything's going on in the feature demon room. So the decision demon takes a look at who's getting the most complaints and says, well, we've got to be looking at an R. So new fonts can be explained, and our immediate recognition can be explained in terms of the Pandemonium model. So what can we do? We can recognize the R in this font. Template model and the Pandemonium model predict that we can recognize that R in the first font, predicts that we can recognize the R in the second font. We can recognize the R in the first font. We can recognize that second R in that second font. Template model says, nope, we should not be able to do that. Pandemonium model says, yes, we should be able to do that. And that's the kind of evidence that we get in cognitive psychology to decide between the possible strategies at that representational level. So as silly as it sounds, as uncomfortable as it might think, that a model that sounds weirder, that says that you have demons in your head, is doing a better job by far than the actual template model. And that is why the Pandemonium model replaced the idea of that template model. All right, so any questions on that? Any comments on that before we just leave this with a few challenges that I'm gonna send your way? Yep.
I don't know. I think I'm just skeptical of thinking that there's demons in my brain, in my mind. Did Selfridge actually say that there were demons, or is this an easier tactic to get us to understand the topic?
Selfridge actually proposed it in this way. It has since, I mean, the demons have since been dropped in terms of making the model more, I guess, simplistic and streamlined. The problem with this, and one of the reasons that I choose this is because it's so kind of provocative, is that the concept of demons comes with a lot of other stuff, right? So you don't, if you came up to somebody and said, hey, would you like a whole bunch of demons in your mind? That person would say, no, thank you. But this kind of a setup is actually, you can change it very easily, get rid of the demons. And you could actually change the word demons to detectors, and you would get very close to one of the models that they have for letter recognition right now. So I think it was initially proposed this way. It was kind of explained this way. It is a little tongue in cheek. I don't think Selfridge actually thought of it in this or literally thought it was that way. But that's one of the nice things about representational strategies. You don't have to, they don't have to be literal in the sense that you actually have these demons in your mind. And also, we, as far as some evidence suggests, we do have things in our mind that react like the feature demons react. And we have things in our mind that react like the cognitive demons react. So we can drop the demons and still keep the structure of the theory intact. But also as a sort of just mnemonic device, I think it's a lot more understandable and a lot more memorable to say things like, well, there's feature demons and they get angry, so they call their cognitive demons, rather than there are feature detectors and they have certain weights attached to their connections to cognitive detectors, and those weights are either additive or subtractive. And I mean, that's getting more towards the implementation level of it, which is, again, something that we don't really need to worry about in the cognitive psychology realm that we're in. Any other comments, questions on this? All right. So bottom line, if you have a strategy that you think is used to do cognition and it sounds ridiculous, remember the demons and how powerful this explanation is. It might sound ridiculous, but it might just be our best way of trying to understand a very complicated underlying principle that might not be as easily understood if we get very technical very quickly. All right, so the last thing that I want to talk about with the Pandemonium model, and this is one of the big features of models, is that they suggest questions to ask that might not be readily apparent if you're just sitting in the computational level and you're just looking at, we can recognize different letters. Once you have a model, oftentimes that model just sort of pushes you towards asking certain questions that you would not have asked if you didn't have the model. So for example, when you have the Pandemonium model, you might say to yourself, well, what happens, are there any letters that would be more confusing than other letters, right? You might say to yourself, well, will there be confusion when you're looking at the letter P? Now, we're going to restrict that to just this simplified model. So this is clearly something that is not enough to explain all of our letter recognition. We only have the 4 letters in the cognitive demons. But just to kind of test out your understanding and your ability to work with models, I'm going to leave this as a question for you to tackle. So given this model, this one that we're looking at right here, try to work out after class, will there be confusion if you're looking at P? Or will the decision demon still have a definitive answer that yes, we are looking at a P? And then other things that this type of a model can suggest are things like, well, what happens if we lose some connections due to brain trauma? What if we have some injury to our brain that actually destroys part of our letter recognition model? Will there be confusion when looking at the letter R? So you could take a look at a model like this, and you might say to yourself, well, let's model brain trauma. And what would brain trauma look like? Well, brain trauma might look like dropping your phone and your phone breaks, and now you can't call anybody. So what if that 4th feature demon, that diagonal slash, what if he lost his cell phone and he couldn't call R anymore? What letters are now going to get confused? And what letters are still going to be readily discernible between each other? And this can make predictions about what we should see when people struggle with letter recognition. Certain letters should be confusing, certain letters would not be confusing. And again, that could be modeled with these loss of connections, and those are questions that are become more apparent when you have a model that you're dealing with, which is one of the reasons why these models are so important in terms of how our brains work. And the final thing I want to mention about the Pandemonium model is that certain models, so you remember the 3 levels of explanation, and we're sitting at the representational level. we want to eventually get at the implementation level. And the implementation level is one of the hardest levels to get to. And sometimes you have a model like the template model, and you have no idea how you're going to get it to the implementation level. It's just something that doesn't really map nicely onto what we know we're working with at the implementation level. But if you have something like this, a model like this, you might say to yourself, well, wait a second, those connections, those look a lot like neurons, right? Neuron connections in the visual cortex. So if there are these types of demons in our mind, and we're going to implement them with our visual cortex because those connections kind of look like neurons, can we find actual implemented feature demons in our mind? And it gives you this kind of thing to look for. And that's what I'm going to show you right now. I'll be completely transparent. I really, really hoped that either Selfridge's paper or David Hubel and Torsten Wiesel's paper came out first. They both came out in 1959. So I'm not sure which one influenced which, but you might sometimes get representational level influencing your understanding of the implementation level. You might sometimes get the implementation level influencing your understanding of the representational level. But here we have actual neurological evidence of feature demons. And this was done with studies where they did single cell recordings in the visual cortex of cats that were anesthetized, and then they were shown different images. And I will let Hubel and Wiesel explain what happened and just see that they actually found the implementation of a feature demon.
At the beginning, we couldn't make the cells fire at all. We'd shine lights all over the screen, and nothing seemed to work. And rather by accident, one day, we were shining small spots, either white spots or black spots, onto the screen. And we found that the black dot seemed to be working in a way that at first we couldn't understand until we found it.
So that noise that you hear, that's the actual electrical firing of a neuron that they're recording. So they hook it up to a speaker so that you can hear when the electron is firing. So that kind of like sound, that's when the electron is firing.
It was the process of slipping the piece of glass into the projector, which swept a line, a very faint, precise.
So they're saying it swept a line. It's a little difficult to see, but there is a diagonal line that is getting swept across this cat's field of vision. And that is what is activating this neuron. That is a feature demon. That neuron is the implementation of that feature demon.
Narrow line across the retina. And every time we did that, we'd get a response.
So as you can see, that's the implementation. I'm not sure if that implementation informed Selfridge or if Selfridge's model informed the implementation. It really doesn't matter which direction it goes to because you can get crosstalk amongst all three levels that'll help you understand it. But it just kind of goes to show you that these representational levels, we don't have to worry about how they're implemented. But in order to fully understand a human mind, you do have that implementation level. And Hubel and Wiesel literally found the implementation of that feature demon. So any final comments, questions about the representation? Yep.
What do you think if someone has dyslexia, how will they read? Like, will their future demons be on the ground?
Yeah, so one of the first things to that's a really good question. One of the first things to do is kind of really be clear about what people with dyslexia struggle with. So do you have any insight into that? So I'm not an expert in dyslexia, but from just previous things that I've seen, I do believe that there's a lot of struggle with D's, B's, P's, and Q's. So specifically the lowercase D's, B's, P's, and Q's. There's something about the fact that it's the same shape in different orientations that is very confusing for them. And if you have a dyslexic person who's trying to read and it's filled with those particular letters, that will slow them down. other letters. So that is an excellent question. Using this model, if we were to extend it so that we had lowercase b's, p's, q's, and what did I forget? D's. Yes, D's. How might a typical person's model look different than somebody suffering from dyslexia? Yep. So which demons would be in the wrong spots? It is hard to explain, and this is actually a really challenging thing to do in your mind without writing it down. So, but again, I mean, these kinds of things is what suggests to us features that might not be in this representation so far. So some of the ways that these models are built is you ask yourself, well, what can a human do? And then you ask yourself, does your model explain what a human can do? And then if you find something new, you either find it in your model, like we did with the next different font of R, or you find out that your model fails. And if your model fails, then what you need to do is you either need to change your model. So for the template model, you start adding more templates and more templates and more templates, or you abandon your model when it becomes just, there are certain rules about when to abandon a model that we won't go into, but eventually you just keep adding so much to try to explain things that your model loses all its usefulness as a model, and then you just say, you know what, it can't possibly be this, let's abandon it. But your idea of the demons getting confused and getting crossed over, one of the things that confusion of B's, P's, D's, and Q's would suggest would be that the feature demon with the curve on its belly, we need another feature demon with a curve on their belly going the other way, right? In order to recognize all the letters that we recognize, we would need the reverse twin brother of that particular demon. And if you're getting D's, B's, P's, and Q's confused, then what might be happening and what we might want to look for is those feature demons, the ones with the curve going this way and the one with the curve going this way, they might both be talking to cognitive demons that they should not be talking to. So this demon over here it should be talking to B and it should be talking to P, right? It should be talking to those two cognitive demons. If you're confusing it with Q and with D, that means that it also has in its group chat D and Q. So it might be that people with dyslexia, they have too many connections, and it's specifically some features that for some reason get connected to cognitive demons that they should not be connected to. And again, this gives us a way of understanding the behavior and also a way of understanding what might be going on in representation. And it would also let us know what to look for, right? So if we were Hubel and Wiesel and we were doing single cell recordings in humans, then we would look for cognitive demons where the actual letter gets activity. And then we could look for those feature demons where this feature demon and this feature demon are getting activated. And then we would predict that in a dyslexic individual, this and this are both going to get sent to the letter P when they should not. It should only be this one that gets sent to the letter P. So that's the kind of reason why we have this model, because you can just see, I mean, we don't know. I'm going to assume that none of us really are experts in dyslexia, and none of us in here are really experts in letter recognition. But with a simple model like this, we've been able to reason through how that might actually work and come up with a testable hypothesis that we can actually go forward and would be able to test in the real world. And that's where the power of these models come from. So just knowing this and not knowing anything about dyslexia or anything really about letter recognition, you can start making really powerful predictions. So imagine if, you actually spend years learning the models that are pertinent to a field. It's one of the reasons why cognitive psychology is so powerful and so successful. All right. So any other final thoughts on that? Okay, so one of the things that computers have always struggled with is visual recognition. So if you take a look at the history of computers and the history of programming and what they thought was going to be very difficult and what they thought was going to be very easy and what they actually found was very difficult and what they found was very easy, basically behaviors that humans consider trivial are incredibly difficult, or were incredibly difficult for computers to do. Things that humans find difficult were incredibly trivial for computers to do. So math, difficult for the human mind. Math, super easy for a machine. Letter recognition, trivial for the human mind. Letter recognition, difficult for a machine, up until about 5 years ago when AI really took off. So we are going to start getting into a little bit of uncomfortable territory here, because one of the things that AI kind of pulls at and causes a lot of tension is that if a machine can solve computational cognitive problems the same way that we do, what is left that actually makes us special as human beings? So keep that in the back of your mind. We're going to tangentially kind of get there. But first, let's lay some foundations in our look at artificial intelligence. And we're going to start with the idea of the physical symbol system. So a physical symbol system, I love that term because it's literally what it says on the tin. It's physical, it's got symbols, and it's a system. So let's go through some examples. We're going to start off with the abacus. So an abacus is a physical symbol system, and the characteristics that you need to be a physical symbol system, there's 4 characteristics. The first one is that you need to be physical. You need to be a physically realizable system. So you need to be something that can actually be made, that can actually exist. You have to be a physical thing. The next thing in the physical symbol system is the symbols. You have to contain a set of symbols. So what are symbols? Symbols are physical patterns, actual physical things that can be strung together. So in that abacus is filled with symbols. You got 10 purple symbols on that top row. You got 10 pink symbols on that second row. You got 10 orange symbols on that third row. And those are actual physical things, and they can be strung together in this physical entity. The next part of it is that those symbols and that physical symbol system has to contain a set of processes that operate on the symbols. And if you've never seen somebody operate using an abacus who actually knows how to use an abacus, I'm going to show you right now what those processes look like when they're operating on a set of symbols.
Look at the pens, aren't they kind of beautiful?
All right, and the last thing that these physical symbol system needs is that this physical symbol has to be located, embedded, connected to a wider world of real objects, real things, that is related by designation and interpretation. So first, designation. Designation means that the external reality has to be able to be represented on the physical symbol system. So for example, the external reality of 4 is represented by 4 beads all the way over to the left. And the external reality of 20 is represented by 2 beads all the way to the left. So that's the first thing. Designation is the external reality going into the physical symbol system. So that's half of it. The other half, as I mentioned, is interpretation. And interpretation is taking the symbols and putting them back out into the external world. And basically what that means is that to have this physical symbol system, you need somebody who can then look at this system and say, oh, you got 4 beads at that top row. That means the number 4. And you got 20 beads in that, 2 beads in that second row. That's the number 20. So you're representing 24 of something. And I can interpret those symbols and know that that's what you mean. So you need a way to get the external world into the system, that's designation. And then you need a way to get the symbols in the system out into the external world, that's interpretation. All right, so that's a basic physical symbol system. Let's take a look at one that's a little bit more complicated. So a physical symbol system always has to be a physically realizable system. So the next one we're going to take a look at is computers. So computers, they are physically realizable. We have one right here. You don't believe it? Physical. And it has physical patterns that can be strung together. So if you know about computer engineering, you'll know that the physical patterns are actual electrical impulses that are either on or off. That's why computers are at their base binary code, because you can either have a signal that's on or you can have a signal that's off. If you're interested in something even more complicated, check out quantum computing and what it can do, because it can take a range of values. But for right now, on or off, physical patterns, physically on electrical signal, physically off electrical signal, that can be strung together. There are processes that operate on the symbols. So you can write programs that tell the computer when to switch certain things on, when to switch certain things off. There's processes that operate on those symbols. And then it is located in the wider world of real objects, and it's related by designation. So if I was to write an article in Wikipedia about the physical symbol system, I can designate the knowledge of that physical symbol system into that article. So I can represent the physical symbol system in that computer, and that's the writer. And then somebody can come by and do interpretation, and that's the reader. So somebody can take a look at that article and say, oh, okay, that's what a physical symbol system is. Now I get it. So why are we spending this time on physical symbol systems? Why are we taking this time taking a look at the characteristics of them? Well, it has to go back to Alan Newell and Herbert Simon. And these were 2 pioneers in just in general cognitive science. And they came up with what they called the physical symbol system hypothesis. And that hypothesis is that a physical symbol system has the necessary and sufficient means for general intelligent action. So they were proposing that a physical symbol system can do general intelligent action, general cognition, not just letter recognition, but it can do letter recognition, it can do decision making, it can do language processing, it can do visual processing, it can do it all. It can do general intelligent action. And a physical symbol system where you have something that's physical, something that has symbols, something that has a system for manipulating them, and you can relate it to the world by designation and interpretation, that is what is needed. So that is what is necessary. And it's also what is sufficient. So necessary means that that is what is required. You cannot have general intelligent action without a physical symbol system, something that is physical, something that has symbols, processes, designation, and interpretation. That is needed in order to have general intelligent action. And then they also hypothesized that that is also enough, meaning that you don't need more. If you have those 4 criteria, then you can do general intelligent action. So again, why are we spending so much time on physical symbol systems? Well, we're doing it because there is a very, very important physical symbol system we haven't mentioned yet that we are going to want to try to understand, and that is us. So we are physical symbol systems. So let's see if we tick the boxes. Let's see if we have the criteria. I'm gonna stop that guy's dancing for a second. So we're physically realizable, right? We're here. We actually exist. We're made of matter. So check on physically realizable. We actually contain a set of symbols, physical patterns that can be strung together. At the very least, we have neurons in our brain, and these neurons are either firing or they're not firing, right? So these are the symbols. Your neuron is firing, your neuron is not firing. That can represent or be internal symbols in our physical symbol system. There are a set of processes that operate on those symbols. So neurons can either have excitatory connections or they can have inhibitory connections, and they can have different numbers of connections, and then they determine whether they fire based on those connections. We're not going to go into too much detail about that, but we are going to just leave it there that there is this set of processes that operate on these symbols. And then finally, it's located in a wider world of objects related by designation and interpretation. So designation, let this guy dance again. Designation is basically learning. So this person learned this dance, and that dance is represented in their physical symbol system. So they have designated that dance in their physical system. And then we watch him and we interpret that. And we say, oh, this person isn't running a marathon. This person isn't trying to act as a mime and he's stuck behind a wall. No, this person is dancing. I can interpret that. I know what they're doing. So it's located in that wider world of designation and interpretation. So that means that we are physical symbol systems, and understanding how physical symbol systems operate can go a long way to understand how we actually might operate. Now, the one thing that I kind of glossed over with this is that this is actually the physical symbol system hypothesis. So when Newell and Simon came out with this, this was their hypothesis, meaning that they couldn't prove it, but they hypothesized that a physical symbol system has the necessary and sufficient means for general intelligent action. And the question now is this hypothesis true? So is there a way to show that what they hypothesized is actually true? And it's a massively difficult question to actually prove this. And I'm not going to ask for a discussion on this one because this is, I'll give you a spoiler alert, this is Tony Stark level type of reasoning. Thankfully, we had somebody who did it, and his name was Alan Turing. So this is an image of Alan Turing. He was an English mathematician, he was a computer scientist, he was a logician, he was a cryptanalyst, he was a philosopher, he was a theoretical biologist. He was basically just an all-around genius. If you want to know more about his life, especially his contribution to Britain and winning the war, I highly recommend the movie The Imitation Game, starring Benedict Cumberbatch as Alan Turing. And in that movie, he basically helps design a machine that can decode German messages that are being sent, and that helps Britain win the war. If you recall last time I mentioned David Marr of Marr's tri-level hypothesis and how he died really young, and just kind of thought about where would psychology be if he hadn't have died so young. Unfortunately, Alan Turing died from cyanide poisoning when he was only 42. And the inquest ruled that it was a suicide, likely linked to his prosecution because he was a homosexual back when that was not socially permitted. And he was actually chemically castrated and disgraced in his society. And when you see what he could do and what he did, it boggles the mind of how much better humanity would have been if Britain just said, you know what, we have this guy with this beautiful mind, let's just throw money at him, let's throw resources at him. We would basically be, if you can, I don't think it's even that much of an exaggeration, take the world that we have today and transplant all the technology that we have today back to the 70s. I think that's where we would have been if Britain just got behind Alan Turing. That's just my little rant for the day. But anyways, what does Alan Turing have to do with the physical symbol system hypothesis? Well, what it has to do is that he actually proved it's true. So Alan Turing came up with the Turing machine. And this is a machine, it's a mechanism, it has a finite number of program states. And what it does is it takes inputs and it gives outputs as symbols. It has a finite alphabet. And the most important thing about the Turing machine is that it's not a hypothetical construct. You can actually make one. There's an example of a Turing machine right there. So this simple machine, this is a Turing machine. So I'll show you a schematic of what it is and what it does. So it doesn't do very much, except it does everything. What do I mean? So one thing that it can do is it scans. So it takes symbols, it has a scanner, and it takes symbols as inputs one at a time. So it's got symbols on a tape measure or on a tape there. So you can see the little X's, the little blank squares, the squares with the vertical lines. Those are the symbols that you input into the machine. That scanner scans a symbol. And then the operations are that that symbol is either erased or not. And that's where you get the eraser. And you either print a new symbol or not. So you have the eraser and the writer. And then the final operation is that you either change the state of the machine or not. So there's your machine, machine state. So in this case, this machine has 6 states. And then the next thing that you do is you just move on to the next symbol. And that's what the tape mover is for. And that's all that this thing does. So you can write a program that basically says if you see a vertical line and your memory dial is on 1, you're going to erase that and you're going to write an X and you're going to go to the next one. And if you see, and you're going to change the memory dial to a 4. And if you see a vertical line when the memory dial is 4, you're going to leave it alone. You're going to go to the next one. If the memory dial is 4 and the symbol is X, you're going to erase that. You're going to put in a vertical line and you're going to go to the next one. That's all a Turing machine does. And you can program it based on memory dial position and just doing those operations. So why are we talking about this physical symbol system? Well, just to kind of put a stamp on this, it is a physically realizable system. They have built Turing machines. It contains a set of symbols, patterns that can be strung together. It contains a set of processes that operate on these symbols, write and erase, move on to the next one. And it can be located in the world of real objects related by designation and interpretation. So if you were a programmer that was working with Turing machines, you could program in using those X's and those vertical lines and those blank spaces. You could program in and designate things about the external world. And then if you knew how to read the output, you could read that output and get interpretation based on the symbols that were printed out. So it's a physical symbol system. So what? Why are we bringing this up? We're bringing this up because Alan Turing proved, not conjectured, not made a hypothesis about, mathematically, logically proved that given enough time and enough tape, right? Finite amount of time, finite amount of tape. But if you had enough time and you had enough tape, that simple Turing machine can perform any computational task. Any computational task. If you need that Turing machine to add 2 numbers together, it can do it. If you need that Turing machine to take a derivative, it can do it. If you need that Turing machine to recognize the letter R, it can do it. If you need that Turing machine to do any computational task, it can do it. Caveat, given the processing speed of a mechanical device like that, it might take 40 years for it to recognize the letter R, but importantly, it can do that. And what that means is that if our thinking is a computational task, that Turing machine can do any cognitive task. Any cognitive task. This thing can do any cognitive task. It just needs enough time, and enough tape. So we are going to see the implications of this. But again, this sort of just, I mean, I can't wrap my mind around Alan Turing sometimes because it just doesn't seem like genius like that should be able to exist in this world. And when I saw the movie and when I learned more about his life and when I learned about the Turing machine and how he basically, this guy didn't have computers to work on. He invented computers. This guy had paper and pencil, and he was working in an office with papers and pencils and just scribbling diagrams and things. And when I think about what he did, there is one scene, and if you know me, I'm a comic book fan. There's one scene that always pops up into my mind, and it's this.
Tony Stark was able to build this in a cave with a box of scraps.
Alan Turing basically proved you can have artificial intelligence literally in a room with a box of scraps, right? Scrap paper, just writing stuff out. It's just, it boggles the mind. He literally was Tony Stark. And again, we would have had ChatGPT in the 70s. I don't think that's too much of a stretch if he just could have been supported. So in other words, Turing machines manipulate symbols. They define cognition in terms of manipulating symbols. So this is now a proven strategy for cognitive psychology. So what we can do cognitively is we can go forward with confidence, knowing that analyzing the symbols that come in, the information that comes in, that designation, and then analyzing or theorizing the processes that occur in our minds, the actual manipulation of the symbols, and then the interpretation of the output by other people, that is a proven strategy for cognitive psychology because Alan Turing showed it can explain any cognitive task. And again, not just hypothesizing, proved. Math, logic, airtight, it can be done. So the question that I'm going to leave you with now, and we'll pick this up next time. So any cognitive task, Alan Turing proved it, can be implemented in a Turing machine. What that means is that any cognitive task can be implemented on this computer, because this computer is a Turing machine. It's a very complicated Turing machine, more complicated than the one that we saw, but it's a Turing machine. So what I want you to think about for next class is how many cognitive tasks need to be implemented in a machine before you have mentality or thinking or a mind. So what I want you to just kind of think about is what is a sufficient condition for mentality? So think of it this way. Let's say that you had a startup company and you said to yourself, we're going to make a general intelligence AI system, right? That's what this startup company is going to do. And you hire yourself a bunch of computer programmers and psychologists and cognitive psychologists and linguistics and everybody. And they're working on this general intelligence computer program. And you say, all right, you guys go work on it and bring me, once you've achieved mentality, once you've achieved thinking, general thinking, you come back to me and we'll put it out on the market. So they go away for a day and they come back and they say, oh, we've done it. We've got general intelligence. And you're like, great, what can your computer do? And they go, it can recognize letters of the alphabet. And your answer would be, what else? And if they said, that's it recognizes letters of the alphabet, you would say, go back, do more. So they work for a little bit longer. And you go, and they come back, and they're like, oh, we've done it, we got it. And you're like, okay, what can it do? It can recognize letters of the alphabet, and it can navigate through a room without bumping into furniture. And you would say, what else? And they would say, that's it. And you would say, go back, do more. And this process repeats, and it repeats, and it repeats. And eventually, they're going to come to you, and they're going to say, hey, we have this program, and it can do this, and 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 this. And you're going to sit there, and you're going to say, you know what? You've done it. you have cracked it. That is general intelligence. That is thinking. Congratulations, you've been successful. So my question to you, which we're going to take a look at next time, is how much needs to be done before you would say, yeah, you've done it? And is there a way, is there some sufficient condition where you can say, all right, does your program meet this condition? And if it does, we've been successful. If it doesn't, back to the drawing board, do more. That's what we're going to take a look at next time. So we'll stop it there for today. Any final questions, comments? All right, so that's it. So again, think about what you would need in a machine before you would be willing to say, yes, that is a thinking machine. And we're going to see Alan Turing's solution for that next time. But I'm actually very interested to see whether your ideas are going to be different considering just the world that we live in. So all that next time we meet. But other than that, we're done for the day.